In this lecture, I'm going to give a derivation of sorts of the Boltzmann entropy relation, which is shown there. For a little history background, in the late 1800s, Ludwig Boltzmann, in a number of ways, obtained that relationship, which was just the topic of our conversation today. Um, and proposed that there was a very close relationship between the entropy of the system and the thermodynamic probability omega of the system, uh, which can be taken as the measure of the disorder of the system. Remember, omega, chemists call it the thermodynamic probability, but it's really the accessible number of states for the system, usually a very, very large number. The derivation I'll give here, Boltzmann had several derivations of this relation, uh, but the one that I think is the most general and in my ways is the best was as far as I know, given by Max Planck in 1900. You have to recall a little bit about entropy and the kinds of physical quantities that one has in chemistry and physics. And they're broadly, any physical characteristic can be broadly classified into one of two categories, either an intensive physical quantity or an extensive physical quantity. Extensive physical quantities depend on how much of the stuff there is. You know, volume, for instance, is an extensive physical quantity. Mass is an extensive physical quantity. That's to be contrasted with things like temperature. Doesn't depend on how much of the substance is there. If I take the temperature of an object and then split it in half and then take the temperature of the two halves, well, they'll be the same. Or color is another intensive physical quantity. Obviously, if I have a yellow object, a yellow piece of matter, say gold, split it in half, then both pieces are still the same color. So it doesn't depend on how much of the matter is there. We can quantify those in this context, particularly in terms of the entropy. I'll look at two systems: system one, system two. System one has entropy S1, and it has omega 1 number of accessible states. System S2, system 2 has entropy S2 and omega 2 accessible states. And then if we combine those, maybe have a partition between them and then break the partition, it becomes a system of entropy S and total accessible states of omega. Since entropy is an extensive quantity, S1 plus S2 has to equal S, and we have to figure out what to do with the number of accessible states, but that logic is pretty simple, I think. For every state over here, I have omega 2 states over here, so the total number of states when I combine these systems is omega 1 times omega 2, and those two relations are really pretty much all we need uh, to find an expression for the entropy in terms of the thermodynamic probability omega. Provided we use the following assumption, and that's really the real genius of Boltzmann came into play. He had been led through a series of studies to conclude that the entropy is related to the disorder of the system. And the disorder of the system is related to the number of possible ways it can be arranged, subject to the conservation of the number of particles and energy and maybe some other things. Right? So the number of accessible states and the entropy should have a function between them, and I've called that S of omega. So the entropy of the system S is equal to some function strictly of the number of ways that that system can be rearranged. S of omega is some function that we need to determine, and we can determine those from those previous equations. So I'm going to look for this function S of omega. From our previous results, if you come up here, S of omega is got to be equal to S1 of omega 1 plus S2 of omega 2. And that's the relationship that I have here. So put this function for S, but S of omega is for the combined system. S of omega 1, S of omega 2 are S1 and S2 for the two separated systems. Omega is just the product of omega 1 times omega 2, so this can be reduced to that. And now then we get a differential equation out of it by doing the following. Take the partial derivative with respect to omega 1 of this quantity up here. And if I do that, I'm going to get the derivative of the argument of S with respect to its argument. I'll call that S prime. Times the partial derivative of its argument with respect to omega 1, but that's simply omega 2. The right-hand side, if I differentiate this equation all the way through by omega partial derivative with respect to omega 1, S omega 2 doesn't depend on omega 1, and so I just get S prime of omega 1 on the right-hand side. I can then take of this resulting equation, can take the partial derivative this time with respect to omega 2. If I do that, I'll get the second derivative of this with respect to its argument times the partial derivative of the argument, this time with respect to omega 2. But that gives me just omega 1, and so I multiply that times here. And then using the product rule, it's the derivative of this one times this one, plus the derivative of the first term times the derivative of the second, and the first term times the derivative of the second with respect to omega 2 is just 1. This side is easy because the partial derivative with respect to omega 2, there's no omega 2's over here, so that just becomes 0. And then we can uncomplicate it a little bit just by recognizing that omega, the combined system, is omega 1 times omega 2. And this equation then becomes an equation simply in omega. Omega 1 times omega 2 is omega. Second derivative with respect to omega plus S prime, one derivative of omega. And that's a differential equation that can be solved for S of omega. First thing to note is I can just use the product rule again. And this quantity in equation 4 is simply the total derivative with respect to omega of omega times S prime of omega. Again, it's simply the first term times the derivative of the second plus the derivative of the first term times the second. And it reduces to 4 when I do that product rule here, and you can do that and see that they're the same. And that can be immediately integrated using traditional notation. If derivative of the quantity in brackets is equal to 0, then the quantity in brackets has to be equal to a constant k. I can then solve that for S prime, first derivative, that's just k over omega. And that in turn can be integrated. Integrating both sides, I get S of omega on this side. Over here I'll get k natural log of omega, again, plus another integration constant. So it remains now to just define these two constants. They're universal constants because I have to have the same function S for every system. And we can apply essentially a boundary condition. If there's only one state, then that's possible for all the particles to be in, then omega is equal to 1. And that's a highly ordered state. In fact, it's perfect order, and so there's no disorder in that system. Every particle is in the same state. They're all piled into to whatever that state is. All the particles in it, and there's no disorder in the system. There's nothing jumbled up, and so it's natural to conclude that the S of omega when omega is 1 has to be equal to 0. And if I use this relation up here, put in 1 for omega, natural log of 1 is 0, and so that gives us C is equal to 0. So we're down to this point. We've got that the function is some constant still to be determined times the natural log of omega. It remains to find that constant k. Again, it must be a universal constant. It has to be the same function s of omega that we obtain for every possible system that you might want to look at. And here we can use some dimensionality analysis and just look at the units that k has to be in. Pretty obviously, s over here is the entropy. Omega is a number, natural log of a number is just a number, and so k has to have the same units as entropy. And I always remember this for reversible systems. ds is dq over t, where dq is the heat change. dq is energy, so it's in joules, and T is temperature, so absolute temperature, so it's in Kelvin. And so the units, I like to put brackets around the things, so I'm just looking at the units. The units of entropy is joules per Kelvin, and K has to have the same units and be a universal constant. Well, the only universal constant that we have that has these units is Boltzmann's constant. 1.38 times 10 to the minus 23 joule per Kelvin. And so we identify this K with the Boltzmann constant, which we've been representing in class as K sub B. And we get the Boltzmann entropy relationship. Note, this is not a derivation. I put that in quotes. It's certainly not in the mathematical sense or even in a rigorous sense for physics or chemistry. It's really a plausibility argument. It seems pretty reasonable, but ultimately it's a relation that has to be tested against experiment. And essentially a large number of experiments have confirmed this relationship. And so oftentimes you'll see people that will start their study of statistical mechanics, and they will maximize the entropy rather than, like we did in our development, maximize the thermodynamic probability of the system omega, or really natural log of omega. Well, we'll work a few problems in Boltzmann's relation, but we'll do that a little later. I want to get one more relation, but we'll do that in the next video.